My name is Dhananjay, and today we will discuss heat transfer subject, in which we will cover the conduction heat transfer topic. So now come to the point, that is what will be the learning outcomes of this course. So learning outcome is they explain the principle of heat conduction and Fourier's law. We will see what is heat conduction and what are the law govern this heat conduction. And the second one is by applying the knowledge of heat conduction to evaluate and design engineering solutions. So now come to the first, that is what is introduction part of the heat transfer. So we have to understand what is the basic difference between the thermodynamics and heat transfer. So first, the thermodynamics. In the thermodynamics part, we just deal the energy transformation and equilibrium state. It means we just talk about the how much amount of heat will transfer from one state to achieve another state. But in heat transfer, we will focus the rate of heat transfer and what will be the temperature distribution throughout the process. So again, we categorize the heat conduction in three broader terms, that is conduction, convection and radiation. So now come to the first, we will explain or understand what is conduction. Conduction is nothing, it is the heat transfer in an energy transfer mechanism in which thermal energy is transferred from more energetic to less energetic neighboring particles. It means if we provide heat or energy to a single side of any object, then the heat will transfer or move from high energy to lower energy. And this phenomena is occur by two different principles. First one is the bimolecular interaction and second one is the by drift of free electrons. It is clearly seen from this PPT or this diagram that if we provide heat from at this point, then this particle will energize and get struck to another neighboring particles and transfer heat to his neighboring particles. So heat will transfer from high energy particles to less energetic particles, and again this becomes high energy as compared to neighboring other particles, so it will again transfer heat to neighboring. So this is the phenomenon known as the bimolecular interaction.
Yes, dear participants, please listen me.
And by drift of free electrons.
He is Mr. Shivam, who is the manager of this Siemens Center of Excellence.
Now come to the next, that is Fourier's law of heat conduction. So this law states that the heat transfer rate is proportional to the temperature gradient, and for this heat transfer law, we have some assumptions, that is the flow will be steady state in condition and flow should be in one directional heat flow, and boundary surface are taken as isothermal. It means temperature remains constant throughout the surface of the boundary, and isotropic and homogeneous materials will be present. So these are the some assumptions for valid conducting the Fourier's law of heat conduction. Now come to the next. In mathematical form, we can write it as a Q equals to minus K dt upon dx. Where dt upon dx is the temperature difference of it. We can say the temperature gradient along the direction of the heat flow, and area is normal to the direction of heat flow. We will take the area normal to the direction of heat flow. It means if our heat is flowing in x direction, and then we have to take the yz plane for the area. So, and K is the thermophysical property that is represented by K. So these are the mathematical form of Fourier law of heat conduction. Now come to What is the thermal conductivity? Thermal conductivity is a material property that indicates the ability of a substance to conduct heat. Higher thermal conductivity means material is better at conducting heat. So we can say thermal conductivity is the criteria how much amount of heat and in what rate heat will be transferred. It's mainly depends on the thermal conductivity. So variation of thermal conductivity in different materials. In solids, solids have higher thermal conductivity, pure metals, due to free moving electrons that facilitate the heat transfer, and non-metals have some lower thermal conductivity as compared to the and insulators have very low thermal conductivity, and liquid generally have lower thermal conductivity than solid. And we talk about the gases. Gases usually have low thermal capability because their molecules are far apart, so there will be no vibration, lattice vibration of electrons can participate in the heat transfer phenomenon. So what are the applications of conduction? So we can use insulation material for building an industry where we don't want the heat come across the channel. And the heat sink in electronics, analysis of thermal conductivity in materials, design of furnace and heat exchanger, we can also use the Fourier's law of heat conduction. So now conclusion point is that just we recap the key point. First we study what is the heat transfer, introduction of the heat transfer, then on what mechanism we conduct heat transfer, and then in which one we studies that is conduction. And for conduction, mathematical form representation we use the Fourier's law, and what are these applications that we studies. And now we come to some importance of understanding conduction, that is its energy efficiency, material selection, and thermal design of a system.